Hello everyone. So far we have discussed about various data formats and codes that are used in a computer system, such as binary code or a decimal code or BCD or whatever. We also discussed about an Ascii code, which is an alphanumeric code, which is used to communicate with the computer system by using a peripheral device. All the peripheral devices are based on ASCII format. That is, each and every peripheral device would only understand an ASCII format code. So here a computer system requires to receive an ASCII code, and at the same time it should transmit an ASCII code. You know that the ASCII code is a 7-bit code, right? But try to understand, there is no 7-bit format anywhere. Either in the computer system or in any digital system, there is no 7-digit format at all. About this already we have discussed. If you want to store some bits in a computer system, at least you need to have 8 bits. Already we know that there are two registers. One is input register and one more is output register. These input register and output register are of 8 bits in size, in which when an ASCII code is transferred, it occupies the least significant 7 digits. But at the same time, we need to ensure that we need to add a one more digit to make a complete 8 bits, because 7-bit format can never be understood by the computer system. Inside the computer system, either in the input register or in the output register, the system uses these additional digits as flag digits. What is a flag digit? This additional digit in the input register is called input flag. The additional digit in the output register is called output flag. Why the reason we need to use a flag? The moment input flag is set to 1, that instructs the computer system, there need to be a transfer from this input register to the main memory, since the user transferred a 7-bit character to this input register. Let us try to understand once again. Let us say you just try to communicate with the computer system. When you press a character, you know that this character must get eventually transferred to the main memory. But initially it will get transferred to the input register. But from there, system need to make a transfer from this input register to the main memory. But system doesn't aware that a character has been transferred, because this is an automatic transfer that will happen by using an interface. Let me not talk about the interface right now. Let us understand that the moment you typed a character, understand at this point of period that this character will automatically get transferred the moment you type to the input register. But system doesn't aware of the fact that a character has been just generated and transferred to the input register. Since the input register is not the destination of the data, system need to make a transfer to the actual destination, that is main memory. So now the moment the character has been generated, system has to make a transfer from input register to the main memory. So we will use the additional digit as a flag. This flag will be set to 1 the moment a character has been transferred. The CPU watches these flags regularly. The moment one of the flags are set, immediately it is going to make a transfer. This is how we are going to use this flag. When an output flag is generated, when an output flag is set to 1, then the system has to make an output transfer. Primarily, you need to understand that these additional digits in the input register and output register are used as flags. Now, but during the transmission, of course, we don't have any flags. That is, when you type the character, that character will produce a 7-bit ASCII code. This 7-bit ASCII code should need one more digit to make it a complete 8-bit packet. This additional digit can be sometimes a parity digit, which already we have understood. That is, a parity bit is attached to a message to understand, rather to detect, if at all there is any error within the transmission. About this parity digit, you just go and observe the error detection code. You just go and just access this error detection code section of the session of my lectures. this parity digit will be attached. This parity digit, as I told you, it's an additional digit, which is primarily used to identify if there is any error in the transmission. This is what the parity code is all about. Sometimes more bits will get appended. We will understand about those bits in IO architecture, input and output organization. Now let us understand about some other codes that may get used in some digital system. You know about a Bcd code, right? This Bcd code is simply a decimal code. There is no difference in between Bcd code and decimal, because this Bcd code is a binary coded decimal. The only difference is the regular decimal values will get represented in their respective binary equivalents. This 6 equivalent is 0110. 7's equivalent is, this must be 111. Yeah, 7 is equivalent is 0111. So 76 in Bcd will be 0111 and 0110. You know what is Bcd already. Since the computer system cannot understand decimal directly, we use Bcd, which is a binary format for a decimal. But sometimes there is something called Ebcdic. Ebcdic gets used in some of the systems. This could be considered as either an alphanumeric code or a variation of the decimal code. Let us understand what is Ebcdic. This Ebcdic uses 8 bits for each character and a 9th bit for parity. Ebcdic has the same character symbols as ASCII, but the bit assignment to the characters are different. When the alphanumeric characters are used internally in a computer for data processing, it is more convenient to use a 6-bit code to represent 64 characters. A 6-bit code can specify the 26 uppercase letters of the alphabets, numerals 0 to 9. And of course, in addition to which, we also can represent 28 special characters. This set of characters is usually sufficient for data processing purposes because, see, ASCII code is a 7-bit character. 7-bit character is too long. Sometimes you don't require all the characters that are being represented by ASCII code. There are a few systems, embedded systems, doesn't require complete ASCII code. In those embedded systems, we may use Ebcdic, in which the ASCII character is just 6 bits. Okay, and it is not actually the ASCII character, rather it is just 6-bit code, which is more than capable of representing all the letters, uppercase and lowercase, and 28 special characters which are just needed to process some character information. These sets of characters are usually sufficient for data processing purpose, as I told. Using a fewer bits to code the characters has the advantage of reducing the memory space needed to store large quantities of alphanumeric data. I hope you got it. That is, when you use this Ebcdic, of course, in some embedded systems, it reduces the storage requirement to store a character, because Ebcdic is just 6 bits, right? If it is 6 bits, the storage requirement of the main memory is way lesser than the actual ASCII character. So when you deal with some systems which are limited in performance, rather limited in usage, if it is not a complete computer system, rather a processor which is attached to perform a little things such as the microwave oven or washing machine, the processors are simple. These are called embedded processors. These embedded processors, when they try to communicate with the outer world, using the ASCII code is too lengthy. For this reason, we will use Ebcdic, which is a 6-bit character. Thank you.